Okay. So we spent a lot of time last class talking about acid strength, and now we're going to talk about how we can compare the strength of various bases, right? A base being our proton acceptor. All right, so a strong base is going to be something that's very good at accepting protons. And maybe even this word accepting is a little bit too nice and neat. A strong base we kind of think of as something that's stealing protons away, right? It's able to pull a proton off of a proton source. A weak base does not really want to be protonated. It's like, I'm cool. I'm more than happy without that proton. All right, so first of all, there's this correspondence between how strong an acid is and how strong its conjugate base is. So let's take a second to put down some examples here. This is what we worked on last class, kind of review from last semester, being able to get our conjugate bases. All right, I lied. Let's switch this around. Let's do bases and their conjugate acids. Okay, so I'm going to put down some bases, and you're going to tell me what the conjugate acid is. All right, reminder, when a base does its job of doing a base, it accepts a proton. So we're going to go up in number of protons, right? Rather up in number of hydrogens. But that proton is positively charged, so we're also going to go up in our charges as well. All right, so these are these bases and their corresponding conjugate acids. All right, and we actually had this way that we could look up our strength of our acids very easily, right? Kind of the cheating way to do it, which is to look on that pKa table. So for each of these, I've looked up their pKa. HCl is -7. Acetic acid's 4.8. Water is 15.7, and our methane, CH4, has a pKa of 60. All right, so we put this in increasing order here, which means that where is my strongest acid on this list? At the top or at the bottom? The top, right? The smaller the pKa value, the stronger the acid. So in terms of acid strength, my strongest is that HCl, my weakest is that methane. But we're talking about base strength now, right? That was our topic here. So really what I want to do is talk about how strong these bases are over here on the left-hand side, all right? Remember, what we said makes an acid such a good acid is that its base is nice and super stable. Its conjugate base is nice and super stable. So HCl has such a low pKa value because that chloride ion is nice and stable all by itself. All right, so then if we think about how basic that chloride ion is it going to want to accept a proton, or is it already pretty happy without that proton? It's happy without that proton, right? Likewise, we said that methane was such a terrible acid because its conjugate base over here is very unstable. So what does that mean? Does my carbanion here, is it going to be happy without that hydrogen, or is it going to try to steal a hydrogen from anywhere it can? It's going to try to steal one. So we have this inverse relationship between acid strength and base strength. Okay, in terms of base strength, my strongest conjugate acid points to my weakest base, and my weakest conjugate acid points to my strongest base. All right, so when we're talking about base strength, what we want to note here, what we just illustrated, is that we have an inverse relationship. Oops. Between acid and base strength. Okay. All right, so when we were talking about acid strength, we said that there were two ways to do it, the quantitative way and the qualitative way. And we're going to kind of have the same exact thing here with base strengths. So if we want to do it the quantitative way, we're again going to use that pKa table. All right, but specifically we're going to look up the pKa of our base's conjugate acid. Okay, so let's just put down a few examples here. All right, so here are our bases. And now, in order to look these up here, we need our formulas for our conjugate acids. All right, so everybody take a second and give me our conjugate acid formula here so we know what to look up on our pKa chart. All All right, we're going to increase our number of hydrogens. I'm going to put it out front here because I'm remembering that's how it's listed on our table, not like it would really matter. All right, but increase our number of hydrogens and increase our charge. Same thing over here, increase our number of hydrogens and increase our charge. Same thing with our ammonium, increase number of hydrogens, increase that charge. All right, so now these are what I'm going to go and look up on my pKa table here. Okay. So first, we got my hydrogen sulfate here. H2S hydrogen sulfide, affectionately referred to as swamp gas because it does not smell very good. All right, that one's right there. And our other one, our ammonium, right there, 9.4. Okay, so let's note our pKa's. What do we got? 2, 7, 9.4. All right, so in terms of pKa's, this one was 7, this one was 2, and this one was 9.4. So if I was thinking about acid strength, which one of these would be my strongest acid here? The HSO4. This is my strongest acid. And which one would be my weakest acid? The NH4, the ammonium. So this one's my weakest acid. But again, we got to remember that acid strength and base strength are inversely proportional. So out of these three bases here, which one is going to be my strongest base? The one that corresponds to the weakest acid. Yeah, so this one's my strongest base. And which one's the worst base? The sulfate. This one's my weakest base. All right, so we're going to look up our pKa of our base's conjugate acid. All right, and then importantly, it's the highest pKa that will point to your strongest base, right? We got to remember that inverse relationship. All right. Cool. So again, that's all nice and good. If we can find our conjugate acid on our pKa table, we can use that value to tell us our base strength. But how do we do so qualitatively? All right. Again, we're going to be using that same Fario what are those things called? Acronym. There it is. Remember, this was just this helpful thing of these 5 properties that we help keep in mind to tell us about the stability of a conjugate base. And the order is the exact same here. Again, the most important is that formal charge. The least important is that orbital. All right, but now instead of looking for the most stable conjugate base to tell us what our strongest acid is, we want the least stable molecule. That will tell us what our strongest base is. All right, so we're looking at the same exact things, but we're trying to now determine which one's the least stable. That would be our strongest base. All right, so let's just do a bunch of examples here. So we're going to compare and determine what is the strongest base. All right, so I'm going to put down a few examples here, and I want you guys to go through and try to tell me which one would be the strongest base that we would have. All right, and in addition to which one's stronger, I want you to tell me why, meaning which one of those FARIO acronym features is what led you to that conclusion. All right, so let's go through these. So we'll call these first ones A and these second ones B. Who thinks that A is our stronger base? And who thinks B? Okay, great. So indeed, it's going to be A that's our stronger base. All right. This one over here is more stable. And why is it more stable? Which one of our FARIO acronyms? Formal charge. But remember, when we're talking about base strength, the stronger base will be the one that's the least stable. All right, so that's what makes this one our stronger base. This one's more stable. That means this one's our stronger base. The exact opposite consideration as what we were applying for our acids. All right, A or B, what do we think? Stronger base. Who thinks A? Who thinks B? It is B. Okay. So what was it that made the chloride ion more stable than the fluoride ion? Going down the column, right? And so when we go down the column, what is it that we're comparing? The atomic radius, the size of those atoms, right? So this one here is more stable, okay, because of atom size, which again means that the other one is our stronger base. All right, and then the last one here, A or B, which one's our stronger base? A, and that means that B is more stable. Why is this one more stable? Because of resonance. Which again, this one's more stable. That means that the other one is our stronger base. So we're going to apply those exact same considerations. Formal charge, atom electronegativity and size, resonance, induction, orbital. But we're going to do the exact opposite consideration, where instead of looking for which one is more stable, we're looking for which one is less stable, right? If it's less stable, that means it really wants that proton so that it can be more stable. Cool. All right, so now we're going to do what we call, this is kind of the everything I could ever ask you about an acid-base reaction. So we're just going to lump this all into predicting acid-base reactions. All right, I'm going to leave some room up at the top here for some notes about exactly how we're going to do this, and I'm going to put our example problem down here at the bottom. All right, we've talked a lot about acetic acid. Let's do chloroacetic acid for fun here. And then NH3 ammonia. All right. So the first thing we want to do is get a balanced chemical equation here. I sort of drew big, so I'm going to do my products down here. All right. And you might have some intuition already about what's going to be the acid and what's going to be the base in this reaction. But it stands that both of them could, in theory, play the role of an acid. They both have these hydrogens here that can be donated. We know from our FARIO acronym, as well as some, just review that we've done up until now, you probably already know which one is the base. But let's say that we didn't. We get to a problem where both of these have these donatable hydrogens, and we got to figure out what's going to play the role of the acid and what's going to play the role of the base. All right, that's going to be step one in predicting our acid-base reactions. In order to get our products correct, we have to first determine the acid and the base. Who's going to play what role? All right, you might not always have some intuition about which one's going to be the acid and which one's going to be the base. It might not always be as straightforward. So how can we figure out which one's going to play the acid and which one's going to play the base? Well, we can look up, based on the pKa values, how willing this chloroacetic acid is to give up that hydrogen. And then we can look up for this second molecule how willing that ammonia is to give up that hydrogen. That's what those pKa values are telling us. All right, so what we need to do in order to determine our acid and base is we're going to look up the pKa of both reactants. All right, so going back to our handy dandy pKa table here. All right, everybody take a second. We're going to practice hunting through this thing here. Chloroacetic acid is going to be somewhere in the middle here, so take a second to get that pKa value. Anybody got it? The 2.8, right? So here's our chloroacetic acid, 2.8. All right, and then we need ammonia, NH3. I'll tell you that's going to be in this last column over here. What do we got? 36. Okay, so 2.8 and 36. In terms of my pKa, right? So what these pKa values tell me is which one of these two is the stronger acid. Which one's the stronger acid? The one on the left or the one on the right? The one on the left, the chloroacetic acid. So then which one do we think is going to play the role of the acid in this reaction? The stronger acid, right? Whichever one's the stronger acid is going to be the acid in your acid-base reaction. Ammonia can play the role of an acid, but it's a pretty shitty acid, right? This thing's a really good acid with its nice and low pKa value, so that's the one that's going to play the role of the acid in my chemical reaction. And this one will play the role, the other one then plays the role of the base. All right, so they both have these donatable hydrogens. So in theory, they could both play the role of an acid. So I'm going to have to look up, based on that pKa table, and figure out which one's actually going to play that role. Okay, so look up the pKa of both of our reactants. The stronger acid is the acid in your reaction. Okay, now that was an important first step, because once we do that, now all of a sudden we can predict our products. Okay, so that's step 2. Now that we've done that, you're going to predict your products. And that just goes back to our discussion of those conjugate pairs. Right? Taking that structure for your acid and donating that proton, taking your structure for your base and accepting that proton. So everybody take a second and give me my products of my reaction here. right, so my chloroacetic acid donates that proton, meaning that that oxygen has that -1 formal charge, so it's got 3 lone pairs. My ammonium accepts that proton, so now my nitrogen has 4 bonds and it has that positive formal charge. Okay, cool. So now we can go a step further here. We can now draw that reaction mechanism. Meaning we're going to put in those electron pushing arrows. All right. So looking carefully at our chemical equation here, what bond is broken in this chemical reaction? The OH bond. And what new bond is formed in this chemical reaction? The NH bond. All right, cool. Well, this pair of electrons here that I colored in orange, my bonding pair between oxygen and hydrogen, where does that pair end up going on my product side? To the oxygen. So it was a bonding pair, and now it's a lone pair. And likewise, where did this pair of electrons come from that makes up my nitrogen-hydrogen bond? It was this bonding pair. It used to be the lone pair, all right? And so this is what our electron pushing arrows are going to show. Our new bond being formed, so we're going to need 1 bond formation arrow, and we're going to need 1 bond breaking arrow in order to do our mechanism for this acid-base reaction. So see if you can't put in those electron pushing arrows. So we have this bond formation arrow here starting at that lone pair, going to that hydrogen atom, and then we have our bond breaking arrow starting at that bonding pair and ending at that oxygen atom. And you'll always have these same 2 arrows in your acid-base mechanisms here, all right? So we need a bond formation all right, starting at that bases lone pair, giving us that new base hydrogen bond. And we'll always have 1 bond breaking arrow. Starting at that acid hydrogen bond and becoming just a lone pair on that, what is now your conjugate base. All right, so bond formation, lone pair becoming a bond breaking, a bond becoming a lone pair. Cool. All right, so we know what's playing the role of the acid or the base. We know what our products are. We can even show how the electrons are moving in order for this reaction to occur using our reaction mechanism. There's one more thing that we can do, and that is to determine the direction of equilibrium in this reaction. All right, a big part of your Chem 1B course was kind of reprogramming your brain to not just think about chemical reactions as always going from reactant to product, but going in both directions at the same time. right? So reactants can combine to form products, but our products can also combine together to go back and form reactants, all right? And when we mix these two things together, we don't know how much of this reaction is actually going to occur, or if not much reaction is going to occur at all, and our reactants are just going to sit there mixed together, right? And we use this equilibrium calculations to determine that, okay? So what we can do here is sort of the same thing. What we're going to do is calculate the delta pKa. All right, your delta pKa is the difference between the pKa of the conjugate acid and the acid. All right, so first of all, what is my conjugate acid here? I got this pKa. Is this my conjugate acid? No, that's the base of my reaction. In fact, this pKa is kind of dead to me now because, like, great, it told me that that one was going to be the base, but that means that that number is not going to factor in anyway. That proton didn't get donated. So which one of my two products am I going to be looking up here? The one on the left or the one on the right? This one's my conjugate base. This one's my conjugate acid. So I need my ammonium, my NH4's pKa value. So we're going to go back to our table here. All right, looking in that first column, take a second and tell me what the pKa of that ammonium is. At 9.4, right here. Okay, so my pKa, 9.4. I am not going to be looking up a pKa for my conjugate base because it doesn't have a pKa. There's no donatable hydrogen there. And even if there was, it's not going to factor into my decision here. I'm going to compare how strong my reactant acid is to how strong my product acid is. That will tell me which direction this reaction is going to go in. All right? So if we look carefully here, we're going to compare again the pKa of our acid to the pKa of our conjugate acid. Which one is the stronger acid? Reactants are products. What do we think? Who says reactant acid? Who says product acid, right? So again, the one with the lower pKa is our stronger acid. So then which one do we think is going to win at pushing this reaction in the other direction? The stronger acid or the weaker acid? The stronger one wins, right? So yes, this reaction here will be pushed in favor of that product. The stronger acid wins. So if I did my little equilibrium arrows here, I could kind of show we favor that product more than our reactant. But we can actually go a step further because the pKa is directly related to those equilibrium constants. All right, so for our delta pKa, what can we say about our equilibrium? If you remember when we were talking about equilibrium, we had these cutoffs where we would say it was either strongly or weakly favoring one side or the other. And that was 10 to the 3 and 10 to the minus 3. Well, a pKa is now put on a log scale. So we're going to take the log of those values, all right? So if it's less than -3, we would say that strongly favors your reactants. If it's between between -3 and 0, we would say that weakly favors our reactants. Between 0 and +3, that will weakly favor your products. And if it's greater than 3, then it would strongly favor the products. All right. So in this case here, what would we say about our equilibrium? We said it favors the products. Does it strongly favor the products or weakly favor the products? The difference between 9.4 and 2.8 is 6.6. Yep, greater than 3. So we can just represent this with that one arrow saying it strongly favors our products. All right. In fact, we can go back to our Chem 1B, and honestly, I'm just kind of going to tell you this as a fun fact. I'm not going to expect you to do any math here, but it turns out that the equilibrium constant for this reaction here is just simply 10 to that delta pKa. So 10 to the 6.8, we get this ginormous number for our equilibrium constant. You can even do a little bit of math using your ice tables, and you could find that in this reaction here, 99.95% of all of your acid molecules will react in order to get your conjugate base here, right? So this reaction here very efficiently goes to the product side. Okay, I'm not going to expect you to do that. I mean, if you want to have fun with ice tables again, go for it. This is what I'm going to expect you to know, is that we can figure out the direction that that equilibrium lies by calculating that delta pKa. And that difference between those two pKa values, specifically the pKa of your conjugate acid and your acid, tells you just how strongly or weakly it favors the products or reactants. All right, so pretty much every single piece of information we could know about an acid-base reaction pictured here. All right, what's the acid, what's the base, what are our products, what's our mechanism, and which direction does our equilibrium lie in? All right, let's do another one. So this one y'all are going to do from scratch here. Again, two molecules with donatable hydrogens. So step one, we got to figure out what our acid and base are. Then we can go about predicting our products, putting in our mechanism, and then finally looking stuff up to figure out which direction our equilibrium lies in. All right. I lied. We're going to mix it up. We're going to make this, instead of just ethanol, we're going to do trifluoroethanol. Stick some fluorines on the end here. All right, so that pKa table is under the introduction page on Canvas if you want your own personal copy. I will put this one up here. I'm pretty sure everything is on this second page. Yep, in fact, I can even zoom in a little bit. All right, but I'm gonna give you guys a few minutes to go on your own. Try to take this all the way to the end here, telling me, doing those 4 steps. Figure out your acid and base, predict your products, put in your electron pushing arrows, tell me which direction that equilibrium lies in. All right, so I'm going to look up my two reactants here. All the way on the wrong part. Jeez Louise. Okay. All right, my pKa, I forgot it now. 12.4? 12.4. And for my second reactant, that pKa is 36. So which one's going to be the acid, the 12.4 or the 36? The 12.4. My stronger acid is my acid. The other molecule will then play the role of the base. All right, we could do our products first or our electron pushing arrows. It doesn't matter the order for those next two steps. Importantly, since this is the base, it's going to reach out and grab that proton, leaving that pair of electrons on that oxygen. Okay, so my mechanism here, I got my bond formation and my bond breaking arrow. My oxygen with its 3 lone pairs and 1 bond will have a negative formal charge. My nitrogen with its 4 bonds will have a positive formal charge. All right, so then the last step, this is my conjugate base. This one's my conjugate acid. In order to figure out which direction this reaction goes in, we're going to have to look up our acid pKa and compare it to our conjugate acid pKa. So I got one more that I'm going to go and look up here. That's that 11.3 for the protonated form of that molecule. Okay. So again, let's figure out which direction this equilibrium lies in. And so according to our comparison between our acid pKa and our conjugate acid pKa, this reaction favors which direction, the products or the reactants? The reactants. And does it strongly favor the reactants or only weakly favor the reactants? It will weakly favor the reactants, right? So I can draw my little unequal equilibrium arrow here, kind of showing I'm still within that dynamic range, but this does weakly favor the reactants. All right. So weakly favoring means we still do get some product formation. So we'd get about 22% products here. The other 78% would still be our reactants, roughly speaking. So we do get some product. It's only weakly favoring the reactants. But at equilibrium, yes, majority of those molecules are still in that original form there. Okay? And again, I got these numbers just by building an ICE table and assuming that we started out with equal amounts of this and this. I don't expect you to get these numbers here, but just kind of want to reinforce what we mean by strongly versus weakly. Cool. All right, so then one more that we're going to do here, because again, you might have had a sense of what was going to be the acid and what was going to be the base, but that's not always the case. Okay, so we're going to look at a molecule. We call this phenol. And we're going to look at hydrogen phosphate here. This is one that has that expanded octet. So HPO4 minus here is the Lewis structure that I've drawn. We got to draw out our Lewis structures if we're going to do our mechanisms. And again, both of these have these donatable hydrogens, and it's probably not super obvious just by looking at them what's going to be the acid and what's going to be the base. All right? So again, let's figure out which ones are acid and which ones are base. Let's predict our products and put in our electron pushing arrows. And then lastly, let's figure out what this equilibrium is. Does it favor the reactants or the products? I'm going to give you another minute or so to copy this down, and then I'll put up that pKa table. So here's our phenol, and here's our hydrogen phosphate. All right, so that means that this alcohol here, this phenol, is going to be playing the role of the acid. And hydrogen phosphate is going to be playing the role of our base here. So when we do our products, our acid is going to lose that proton, giving that oxygen a negative charge. That base is going to gain that proton. I actually got a bunch of different oxygens here. All right, which one do we think we should put the hydrogen on? The one that's neutral or the one that's negatively charged? The negatively charged one, right? That'll be more basic than that neutral one. It wouldn't matter which one of those negatively charged ones you picked. It would have been equivalent. But here we go. Doing my reaction mechanism, I'm going to do my bond formation arrow from that lone pair to my hydrogen, and then my bond breaking arrow from that bonding pair onto my oxygen. So here's my mechanism, and now last step is to figure out our equilibrium. All right, and for that we're going to need to look up our conjugate acid. Which one's our conjugate acid, left or right? The one on the right with that proton. And that we actually need to scroll up to this other page here. All right, in this last column, shout it out when you find it. That's 6.7. All right, there's our H2PO4 minus. Okay, so then everybody just take a second. We're going to be favoring our reactants or products. Comparing our acid with our conjugate acid. Which one's stronger? The conjugate acid's stronger. So what does that mean? Does it favor the products or the reactants? So you're always going to go, right, the stronger one wins, meaning you're going to go in the direction of the weaker acid, which is in this case towards our reactants here. And in this case, if we take our difference, does it strongly or weakly favor our reactants? So this one would strongly favor our reactants. Meaning that if you mix phosphate and phenol together, nothing much happens. All right. Again, we can do our ice tables and do our math. 98% of those molecules remain unreacted, and we only get about 2% of our product that's formed here. Only about 2% of those molecules will undergo any acid or base reaction. Cool. All right. So, talked about base strength being inversely proportional to acid strength, and then also about predicting our acid-base reactions, which is kind of just like everything I could ever ask you about an acid-base reaction. We mix two molecules together. What's going to be the acid and what's going to be the base? Once we figure that out, we can predict our products and draw our reaction mechanism. And then lastly, we can calculate our direction of equilibrium by looking up our conjugate acid pKa and comparing that to our acid's pKa. Cool. All right.